Welcome to a One Finite Planet EV video on regen braking. There are chapters on workings of regen, the 3 ways to activate regen braking, and busting 3 common myths. Separate videos will be linked below on the Tesla approach versus the BYD/Porsche approach to regen, and on using regen to maximise range and economy, but they're both built on the foundations laid down in this video. First, the basic physics. A moving vehicle has kinetic energy, and as energy is never created or destroyed, braking or slowing down reduces kinetic energy, and that requires converting some of the kinetic energy into another form of energy. Friction brakes convert kinetic energy into heat energy, increasing heat within the brakes. This means friction brakes can only work when there is room for more heat in the brakes, and friction brakes fail if overheated. Powerful friction brakes require, first, a lot of force to be able to create enough friction to convert significant kinetic energy into heat, and second, materials capable of withstanding that heat together with sufficient ventilation/cooling to dissipate the heat and avoid the brakes overheating. Energy, e.g. kilowatt hours, is power, e.g. kilowatts, multiplied by time. So power is the rate of flow of energy. Braking with a force equivalent to maximum acceleration from a 100 kilowatt engine will generate heat at the rate of 100 kilowatts. That braking force will require the brakes to dissipate heat equivalent to what would be produced by a 100 kilowatt radiator. The slower a vehicle is moving, the less energy to be converted, so the less heat generated. With friction brakes, friction between calipers/discs or drums and shoes becomes ever more effective as speed decreases, which makes friction brakes increasingly effective as speed decreases. This is why new drivers have to learn to ease up on the brake pedal when coming to a stop, if they avoid the brakes becoming too effective at low speed and cause a jerky, premature stop. Regen braking works by converting kinetic energy into electrical energy. Most EVs use permanent magnet AC motors, as discussed here, and although some EVs also use induction motors, which adds some complexity to regen braking, and that's covered in a video on EV motors linked below, but the basic principles are still the same. A further simplification is that while the frequency of AC relates directly to motor speed, the power as AC at all has little impact on regen, as the first step in regen systems is to convert the AC to DC. So AC frequency from the motor doesn't matter either. This reduces the functions of EV motors to be considered as just 2 modes. 1, supply voltage to an EV motor to force the motor to spin. 2, force the motor to spin to generate voltage. Motors convert power. Electric in, kinetic out, kinetic in, electric out. Electric drive happens when voltage supplied to the motor causes the motor to spin, and thus also the wheels that are connected to the motor to spin. The power to maintain the voltage consumes electrical energy, which is needed to accelerate and to overcome air resistance. When the motors are not powered, the car's motion spins the wheels, which causes the connected motor to spin and generate voltage. But regen braking requires using the energy by having the voltage generated connected to an electrical load that consumes power. An electrical load allows current flow, and combining voltage and current in the classic P equals VI, where P is power, and power for any time equals energy. And a way of consuming the electrical energy is required to avoid the equivalent of overheating in friction brakes. For regen braking, attaching a load to the voltage is like the pressure that creates friction, and you need to consume the resulting energy created from resistance to the motor spinning, just as friction brakes need to use up or dissipate heat energy. Regen braking must use up electrical energy. While you could power lights or something, for regen braking, the goal is to use the energy to charge the battery. The point of all this is the power of regen braking is determined by the ability of the EV to transfer energy from the motor being turned by the wheels within an electrical field and store the energy in the battery. Just the spinning of the motor won't result in braking effect unless the circuit has a load to create the power, and the power must be consumed for the load to continue to consume power. In this case, the brakes only work while the power can be sent to the battery, and the power of the brakes is limited by the rate of power or charging the battery can take. The regen braking effect comes from the power created by spinning the motor being used up, just as friction brakes need to use up or dissipate heat energy to remain effective. Regen brakes must use up electrical energy to remain effective. If you have an e-bike or e-scooter, you can try pushing it when it's powered off. There's resistance to getting started as it requires energy to ramp up the voltage provided by the motor. But at constant speed, there's negligible braking effect from the motor without power, unless the voltage generated is powering something. The braking effect will occur no matter what consumes the power. So you could use the power for lights or something, but regen braking is using the power to charge the battery. This results in some key characteristics of regen braking. First, the power of regen braking is limited by the maximum rate the battery can take charge, which is reduced when the battery is not at optimum temperature or is at near full charge already. Second, the faster the car is moving, the more power available to be stored, which makes regen braking potentially the most powerful at high speeds, and less effective as speeds reduce, making regen braking a good complement to friction brakes, which follow the opposite pattern. Third, below speeds that will produce the minimum voltage for charging circuits, you can't create a load, so regen braking becomes totally ineffective. The first way to use regen braking is to let the car do it. Automated systems, from adaptive cruise to self-driving, all depend on the vehicle computer being able to control the brakes. In an EV or hybrid, the computer can control both friction brakes and regen braking, and will use regen braking whenever possible in priority over friction braking. This reduces wear on the friction brakes and maximizes efficiency. Maybe one day, most driving will be automated. For the absolute technically optimum use of regen braking, let the computers drive the car, or at least let the computers control the speed using adaptive cruise control. But where's the fun in that? What about driver controls? The second way to control regen braking is, somewhat ironically, via the accelerator pedal. Braking force controlled by the accelerator. Go figure. Should it be called the power pedal or perhaps the motor pedal? This one pedal has long been used to accelerate and decelerate and even to maintain constant speed. Whatever you call the accelerator pedal, regenerative braking that is triggered when a driver reduces pressure on the accelerator pedal, or lift-off regen, is often mistakenly seen as the only regen braking. And while lift-off regen is not the entire story of regen, it is the new and fun driving experience enabled by regen. Regen braking on liftoff was initially added to EVs to create a similar feel on liftoff to that caused by engine braking of a combustion engine, which is an inherent characteristic for those engines resulting from kinetic energy being converted to heat as air is compressed within the cylinders. With EVs, as there is no inherent engine braking that will determine the level of liftoff braking, this makes the level of liftoff regen braking a design choice that just gets implemented by software. Most EVs offer a choice of liftoff regen levels, which can range between 0 liftoff regen and up to around 77 kilowatts of regen braking, as chosen as the maximum by Tesla, as this level is seen as the maximum passengers are happy to be thrown forward in response to the driver lifting off on the accelerator. Any EV capable of charging at more than 77 kilowatts could almost certainly offer an even higher level of liftoff regen than the options provided. For example, as explained by Tom Mologny in the Inside EVs review linked below, the Porsche Taycan is capable of 265 kilowatts of regen power, over 3 times the liftoff regen offered by Tesla vehicles. But Porsche restricts liftoff regen to a much lower level of just around 20 kilowatts. Reviewers often praise EVs with high levels of liftoff regen, seemingly mistakenly believing, even with vehicles like the Taycan, the level of liftoff regen provided is an indication of the vehicle's maximum regen, when in contrast, vehicles that do have very high levels of maximum regen could never allow full regen braking on liftoff. What is real is that many drivers find high levels of lift-off regen a novel and fun experience, despite some brands seeming to believe that high lift-off regen would tempt drivers to overuse regen and result in complaints of vehicles failing to deliver stated levels of economy. The third method to control regen braking is, surprise, surprise, the brake pedal. Many drivers and even reviewers either forget or have never heard most EVs and hybrids activate regen when the brake pedal is pressed, and most also have a brake-by-wire system, which means the friction brakes will not be used until regen braking alone is not enough.
When the driver steps on the brake, the electric motor switches to generator mode. The drivetrain transfers the kinetic energy to the generator, which converts it into electrical energy. This energy is stored in the high-voltage battery. The generative braking torque of the electric motor, which is the result of energy generation, decelerates the vehicle. At low speeds, for example shortly before the vehicle comes to a stop, the electric motor can no longer supply sufficient generative braking torque, and the friction brake must be activated. To maintain the required deceleration, the braking torque from the friction brake is continuously adapted to the current generative braking torque, a process called torque blending.
Further explanation is available in an Engineering Explained video linked below, but with an extract here.
So what is brake-by-wire? Well, essentially it just means that you have electronic control of your brakes. So when I touch the brake pedal, it's not actually, it is creating pressure. I do create pressure when I press on that brake pedal, but that pressure is not doing anything. What's doing something is an electric pump, so it's electronically controlled. So what's actually happening? Well, I press on the brake pedal, and there is a position sensor for that brake pedal. And so when I am actually pressing on it, there is a resistance to that, but that resistance is artificial. So you have essentially a simulator that's simulating that feel for you. And so, the engineers can design this brake pedal to feel however they wish. So they have complete control over that, and there's a simulated feel to it. But what the system is doing is monitoring where is your foot on that brake pedal using a position sensor, and that position sensor goes to a brake control unit, which says, okay, here's how much pressure we should apply to the brakes. Here's much deceleration we want. Now, this is quite common in electric cars and hybrid cars because you also use regen. So when I press on this brake pedal and my desired braking is less than 0.3 Gs of deceleration, well, essentially what the system's going to do is just use the electric motors and just use regen. The mechanical brakes, the disc brakes, aren't going to be doing anything. It's just...
The goal is to make regen braking seamless, which means brake-by-wire is likely to go unnoticed unless the driver notices on the instrument display that power usually goes to the battery when they press the brake pedal. A catch is that while I, Jason, Bosch, and most automotive brands, as per this description by Hyundai, call this BBW or brake-by-wire, it is often claimed that it's not true brake-by-wire if there are any hydraulics in the system, even if the hydraulics are only linked by wire. This is why you can find claims that neither Hyundai nor Porsche nor almost any other brake-by-wire EV or hybrid really have brake-by-wire, because they use hydraulics in the braking system and have a fail-safe which, when activated, results in direct control of the brakes. This is also discussed by Jason.
Now, a lot of people look at this system and say that's not actually brake-by-wire, and I think, well, first of all, it is brake-by-wire. It's what Audi calls it, it's what Corvette calls it, and the C8, it's what all the companies are calling it because it is electronic control of the brakes. The computers have control ultimately. There are certainly varying brake-by-wire systems out there, and I think eventually it probably will be more common that you don't even have a hydraulic system involved, and you can take out some of the complexity of these hydraulic brake systems that are doing, both electronic brake-by-wire and have the full redundancy of the hydraulic system.
Even AI will tell you the industry has it wrong, and vehicles with the system described are not brake-by-wire, and will even more confusingly list vehicles that always used only the friction brakes in response to brake pedal as having brake-by-wire. The only way to really check is to specifically ask about regen alone having priority when the brake pedal is pressed. But to keep it simple, almost every EV or hybrid without a Tesla badge has brake-by-wire. And there are some suggestions Tesla may also join.
Stability program. I wonder if they've gone to a brake-by-wire system, because the brake pedal does feel different. And they said that they've improved the braking performance on the vehicle to allow more energy recapture through the brake pedal. So yeah, before it was a friction brake pedal physically connected. Now it's possible that they either add regen before they get into friction brakes, or there's something with the braking system they claim they've improved. I don't really know what it is, but it requires some definitely looking into the...
Virtually all EVs, Tesla included, use blended braking, which means a mix of both regen and friction brakes are able to be used in response to the brake pedal being pressed. Unlike liftoff, the brake pedal can signal a need for emergency level braking, so even in a Tesla, the brake pedal can access maximum regen beyond what is appropriate for any other scenario other than autonomous emergency braking. Now to regen myths, and the first of the three to be busted here is the mistaken belief that in an EV or hybrid, lift-off regen, that experience when lifting off the accelerator, is the only regen or always the regen that matters most. The true story is that the main benefit of lift-off regen is that it's fun.
I was controlling my speed purely by adjusting the strength of my regenerative braking via these lovely paddles. I didn't have to do that. I could just use the brake pedal. That's still regen braking. It's the same. But it's fun. It's a fun game of efficiency.
There is also a link below to a useful video by Ludicrous Feed that focuses on brake pedal regen in a BYD Atto 3. Tesla aside, the only difference between regen levels is when or if a driver must move their foot to the brake pedal. Although technically the result is at best the same, lift-off regen's more fun and can save needing to touch the brake pedal. Both the strategy of using high levels of lift-off regen and that of using mainly brake pedal regen have advantages. High levels of lift-off regen is just fun, and once you try it, you tend to want it, because it allows making a game out of trying to drive smoothly and avoids needing to press the brake pedal. Downside is it takes a new skill to drive smoothly and efficiently. Sadly, it's difficult to even match the efficiency of brake pedal regen in a vehicle with brake-by-wire, but fun is a reason to want high lift-off regen, at least as an option. The second myth is that use of regen braking can be even better than not braking at all, or at least a general overestimation of the benefits of regen braking, and particularly of high lift-off regen settings. Many people mistakenly believe that the higher the lift-off regen setting, the greater the efficiency, on the mistaken belief that increased regen means increased efficiency. Actual tests often find the reverse, and zero lift-off regen is most often the most efficient, as discussed in the video linked by this thumbnail and to videos linked on here. Here is the conclusion from getting AI to calculate regen efficiency. Although regen braking can limit energy loss to as little as 30%, which is far better than losing 100%, which happens when using friction brakes, you still lose energy every time there is any braking. The smoother you drive, with the least deceleration at any time, the better. Despite recommendations, in theory, Tesla or other vehicles without brake-by-wire aside, the same result should be possible regardless of how the pedals are configured for lift-off regen. Even on a high setting, although challenging, it's still, in theory, possible to coast when desired by keeping the power at zero. That said, while I sometimes try higher settings, I personally always get slightly better efficiency with the lowest lift-off regen setting. Most important is to avoid overuse. Using regen braking when you could avoid braking at all is like thinking you can save by buying things you don't need because they're on special. Myth 3. No, it's not regen braking that brings the vehicle to a stop, because regen braking can't force an electric motor or vehicle to stop. Regen braking works through the retardation as the motor generates electrical power, and unfortunately a stationary motor can't generate electric power. If a stationary motor could generate electric power, then we could create power stations just using electric motors. Free electricity. But sadly, no. The power for friction brakes comes via hydraulics, which ultimately draw their power from the fuel tank or battery. Regen draws its power from the kinetic energy of the moving vehicle, which means brakes powered by regen must lose power as the vehicle slows and loses its kinetic energy. Though simply supplying DC power to a permanent magnet motor, and it will resist being turned, enabling use as a stationary brake. But the motor will get hot over time and will continuously be drawing power while you're stationary. This use of DC, using a form of magnetic locking, can hold the vehicle stationary, but it's not regenerative braking, and instead it's powered braking. Instead of generating energy, holding stationary via the motor consumes energy and drains the battery, even while going nowhere. Just as when stationary, zero electricity is generated, which means zero regen is available, when near stationary, so near to zero energy is generated that the vehicle inverters are unable to produce the voltage needed to charge the battery. There's a minimum. EVs can charge at 100 volt, but probably not 12 volt, and certainly not the 1.5 volt of an AA battery. This need for a minimum voltage for charging means that regen not only becomes less effective as speeds drop, but also there's a speed, typically around 5 kilometers an hour or 3 miles per hour, where regen stops working altogether. This end of regen is exactly the behaviour experienced driving an original Model S or EVs without one-pedal driving. This myth provided another example of AI always trying to say yes, and as a result, giving an ambiguous answer to can regen braking alone stop a vehicle, and suggesting the right regen setting can enable the vehicle to stop without any other intervention. It took asking if stopping by regen alone would break the rules of physics to prompt a clearer explanation. The key point being the last one. As the vehicle slows to near zero speed, the system seamlessly transitions to friction brakes to bring the vehicle to a complete stop, making it appear as if regen braking alone is responsible. One-pedal mode is a complex subject and covered by another video to be linked below, but since one-pedal mode allows the vehicle to come to a complete stop without touching the brake pedal, it becomes common to assume the stopping must be all by regen braking. Note that ICE vehicles with adaptive cruise control also come to a stop without the driver pressing the brake pedal, and the experience is very similar. The strength of regen braking possible is proportionate to speed, as is the ability to generate power. Regen braking does best what friction braking struggles at, but can't do what friction braking does best. There are a few limitations. You can't use regen if the battery is full, but even when starting with a full battery, unless starting at the top of a very steep hill, at every point in a journey, the energy from regen will always be less than the energy used so far, so the battery will always have room. While when braking a battery is unlikely to be still 100% charged, when at near full charge or at the wrong temperature, the same conditions when charging from the plug can be slow, maximum charging from regen, and thus maximum regen, may also be limited. However, most batteries, even near full, can still charge at 30 kilowatts or more, and that corresponds to quite a lot of regen braking effect. To be safe, Tesla, as they use quite high liftoff regen, even added supplemental friction braking to ensure the high liftoff effect in these situations. The more significant limitation is regen becoming ineffective at very low speeds. Given how little kinetic energy there is to be recovered, at these speeds it's not an efficiency issue, but when trying to manage speed by liftoff alone in vehicles not configured to activate friction brakes once regen falls off, it can be annoying. The loss of regen as speeds fall may sound like a bonus for anti-lock braking, but while friction brakes are on each individual wheel, only EVs with 4 motors can offer the same individual wheel control, making regen unavailable as soon as individual wheel braking, as with ABS, is required. Also impacted is hill descent control. In off-road situations, hill descent control at speeds too low for regen braking can be required, and this must either be managed entirely by friction brakes or by powered braking of the EV motor, which consumes power instead of generating power. This low speed limitation also means a vehicle with only regen brakes is not feasible. Technically, the Unagi e-scooter operates on regen brakes alone, but can only do so provided, as is normal with a scooter, the rider dismounts before the scooter actually comes to a complete stop. It also means that in low-speed stop-start traffic jams, regen's not really playing a role. But EVs are still way more efficient because they don't waste energy keeping an engine warm, even when little energy is going into movement. In conclusion, bringing it all together, regardless of how the pedals are configured and how much regen comes via lift-off versus the brake pedal, the sequence is always the same. Regen alone first, then as speed falls, regen and friction brakes, and finally friction brakes to stop the vehicle and keep it stopped. Despite having limitations, regen is a contributor to EV efficiency, and everything counts, but it doesn't even rate on charts like this on EV efficiency, as regen is not at the core of why EVs are efficient, and the benefits of regen are often overestimated. Which pedal is used has pros and cons, as discussed in the video on efficiency to be linked below, but high levels of lift-off regen, as typical with Tesla vehicles, can be novel and means learning the new skill of moderating braking via lift-off. It can feel like a secret, fun skill, and despite being, in theory, less efficient, it appears to have little impact in practice and can be fun. And outside of perhaps in China, Tesla owners do not seem to be calling for brake-by-wire. If you find it fun, why not use high lift-off regen? And if the novelty wears off, or for times you don't find it fun, then, as described in the video on efficiency, in any EV with brake-by-wire, you'll probably gain a little efficiency switching to a lower setting for lift-off regen. As for one-pedal driving, see that video as it's a more complex topic.